Stick with me until the end because the solution to this problem is a true work of art. Nice to meet you. I'm Leo Sacramento, a math teacher, and here on my channel, I solve math problems for you every day. I know it's boring, I know it's complicated, but we're on a really cool, really interesting upward trend. So, guys, please leave your like, subscribe to the channel, share with your friends, and leave a comment. If you also thought this solution was a work of art, or if you solved it in a different way. Alright? Guys, take a look here with me. We have a quadrilateral here. Okay? We have this super interesting quadrilateral here, which we can't. Oops, it froze. We can't say for sure if it's a trapezoid, a rectangle, or whatever. Alright? Where we have 80, 10, and we want to find the value of x. With this segment equal to diff 1. And these two here are equal as well. Okay? Guys, here's a question. When it comes to geometry, if a drawing doesn't label the vertices, the first step is for us to name those vertices. So I'm going to call this one A, this one B, this one C, and this one D. Right? I just named them. It's that simple. Here's something interesting. We have two triangles in this figure. There's this triangle, ABC, and we have triangle ACD. But triangle ABC has a special characteristic. Why? When we look at segment AC and segment BC, they're equal. That's what it's telling me. This symbol here is used to show that the top segment is equal to the bottom segment, right? So if it's telling me they're equal, it's already telling me that this ABC is a triangle we call isosceles because it has two sides of equal length, okay? So for us to solve this, we need to remember a bit about isosceles triangles. Let me draw it here for you. The ruler is broken, but I already bought a new one. It's all its way. Alright guys, let's go. Let me try to draw a nice isosceles triangle for you. Drawing isn't my strong suit. It didn't turn out great. Let me fix that. If we have an isosceles triangle, it's not perfect, but let's fix it. Let's fix it! Now it's a little better. If we have an isosceles triangle with this side here equal to this side, when we draw a Sevian from the vertex where the segments meet down to the base, let's draw this Sevian here. This Sevian is three things at the same time. It's an angle bisector, which in this problem isn't really important to us. It's an altitude, meaning it forms a 90-degree angle. Remember, an angle bisector divides the starting angle into two equal parts. An altitude forms a 90-degree angle when it reaches the other side. And a median, which divides the opposite side into two equal parts. Got it? For us, what matters is the altitude forming a 90-degree angle and the median, which divides it into two equal parts. Alright? So what am I going to do now? I'm going to start here from the vertex segment, C. Sorry, I'm going to draw a Sevian, which is the same one I showed you here. Okay? It's an altitude, angle bisector, and median all at the same time. Alright, so let's draw it here. Let's try to make it look nice here. I don't know if it's exactly at the midpoint, but I'm going to call this point here M. Remember that AB is the same length as DC. That's why there's this little black mark here. So what am I trying to say? That when it reaches the opposite side, it forms a 90-degree angle. So let's form a 90-degree angle. And besides that, it divides this opposite side into two equal parts. But it doesn't give me the measurement of these cents. So let's go. Pay attention here. If I'm calling this x here, I'm not going to use x to make things easier for myself. I'm going to call it a here, for example. From A to M, I can call that a. And since I divide it into two equal parts, the lower part is also a. So the total, do you agree with me, is 2a? Let's write that down here. This total here, I'm going to say it's 2a. Let me see if it's showing up on camera. Perfect, it's great. Okay, now check this out, guys. This is interesting. You have to have a really sharp eye to notice this. This is 90, right? 80 plus 10 is also 90. So we have these two sides here, or rather, sorry, we have these two angles here, both being 90. And both the square and the rectangle are two important quadrilaterals for us to work with, which have angles, all four angles of 90 degrees. Since we can't make a square here, it would be interesting for us to do a geometric construction to create a rectangle, right? And do you think we can do something about that? Let's see. So what am I going to do? If we're making 90 appear on these two sides, let's make 90 appear on the other side as well. How can we make that show up? Following a geometric construction here. All right, I'm going to close this here. Okay. And I successfully closed it right here. That is very nice. Now, take a good look right here. It might not look like it, but AMC, I'm going to call this point N. It's going to be a rectangle. I did it in a way that the 90-degree angle would show up. So I did the geometric construction there. Therefore, this angle down here is also 90 degrees. And we can categorically state that this is a rectangle. Right? Leo, but why did you do that? Why did you make all these changes for this problem? Is this actually going to help me with anything? Well, let's analyze it. Didn't I tell you that from A to B, which measures 2A, is the same length as from D to C? The marking here in black from the original drawing. So if all of this here is 2A from A to B, then from D to C also has to be 2A. Do you agree with me? So let's put 2A here. Dot at? Alright, besides that, I just showed you that I said AMCN is a rectangle. So if it's a rectangle, its opposite sides necessarily have to be equal. So if here, this height here is A, this other height here also has to be A. So it's starting to look good. Alright? Look what's tricky in geometry. You already figured out what I can do here. But for those who haven't figured it out, pay attention here with me. We can call this angle here alpha. Alright? And now look how interesting this is. With respect to triangle DCN, it's a right triangle with hypotenuse 2A and the opposite leg. To alpha, it's A. So we can use this sign. The sine of the angle alpha is calculated as being equal to the length of side A divided by the hypotenuse, which is 2A. Canceling A with A here. So the sine of alpha can only be 1 over 2. And now, if you're already familiar with trigonometry, you can say that alpha is 30. Because alpha is 30 degrees, since it's the acute angle whose sine is 1/2. So what I'm saying here is that this little guy here measures 30 degrees. Now, look at triangle ADC. See? This 30 degrees here is the external angle in relation to this one here. Beauty? He is the angle, external in relation to that. In other words, together they have to equal 180. But there's the exterior angle theorem, which tells me what? The sum of this and the other two interior angles must equal the measure of the exterior angle. That is 10 plus x. It has to equal 30. 10 plus what number goes 3? 20. So we can definitely say that the final value of the variable x is exactly 20 degrees. So here is the comprehensive step-by-step solution to this specific problem, which has been explained beautifully and clearly for all of you to understand. Go ahead and take a quick screenshot of this screen now. And that's it, folks. Comment here if you like this work of art, this solution. Comment, share, like, and subscribe to the channel. And here you'll see the subscribe button and another video where you can watch another lesson of mine. It's okay. Thank you all so much for being here until the end. Warm regards. It cost.